Now next topic, that is Newton's second law of motion for a system of particles. Now see, we discuss the equation MVCM equal to P1 plus P2 plus P3 up to Pn, that is equal to P. Now differentiate this particular equation with respect to time t. So m dVcm by dt equal to dp1 by dt plus dp2 by dt up to dpn by dt, that is dp by dt. So here we can write now m dVcm by dt, that is dp1 by dt, that is f1, force acting on particle number 1, dp2 by dt, that is f2, force acting on particle number 2, like that dpn by dt, that is fn. Now vector summation of the forces acting on each and every constituent particle will give you resultant force acting on a system of particles. So that is equal to F. Or here we can write the same equation like this, m ACM, because differentiation of velocity with respect to time t, that give you acceleration also. So m ACM equal to now F1, that is you can write m1 A1 plus m2 A2 up to mn AN, that is equal to F. Now here the force F, this one, that is the resultant force acting on a system of particles, and that is nothing but the vector summation of the forces acting on the individual particles here. Clear? And A1, A2, A3 up to AN are the acceleration of the constituent particles. Now this equation we can summarize like this, m dVcm by dt equal to dp by dt, that is equal to m ACM equal to F. Now see, dp by dt, that is equal to F, but at present we can't say this is Newton's second law of motion for a system of particles. No doubt, dp by dt equal to F, that we say Newton's second law of motion. But here this resultant force, actually that is the summation of resultant external force and internal force. So F equal to F external plus F internal. But as per Newton's third law of motion, if we think about the forces between a pair of particles, then force on particle 1 by 2 and force on 2 by 1, both these forces are equal in magnitude but opposite in direction. So vector summation will be 0. So in this manner, the resultant internal force between the constituent particles, that will be equal to 0 as per Newton's third law of motion. So here whatever the resultant force or net force appears acting on a system of particles, itself is external force, right? So now we can say this is Newton's second law of motion, because as per Newton's second law of motion, the rate of change of the total linear momentum, that is equal to external force, right? So we can write now the resultant external force acting on a system or system of particles is equal to the rate of change of total linear momentum of the system. So in this way, we derived here the Newton's second law of motion for a system of particles, right? And it is exactly like we discussed for a particle. Clear? So here the center of mass of the system moves under the influence of the resultant external force F. Here we can see F equal to m ACM. Again here, this is the resultant external force, that is equal to mass of a system of particles, but acceleration of a center of mass is appearing here. So here the center of mass of the system moves under the influence of the resultant external force F, as the whole mass of the system is concentrated at that point center of mass. It behaves like that, or in other words we can say center of mass behave like system itself, or we can say center of mass that is the representative of entire system. Now see, here if we take this resultant or net external force acting on the system of particles, that is equal to 0, then we can write dp by dt equal to 0. So P, the total linear momentum of the system, that remains constant. But here this total linear momentum, that is the vector summation of the linear momentums of individual constituent particles. So we can say the vector summation of the linear momentum of individual constituent particles, that remains constant. But here very important thing which you have to keep in your mind, that is this individual linear momentas of the constituent particles may change, but the change will take place in such a way that this vector summation, means the total linear momentum of the system in the absence of resultant external force, that remains constant. So we can say this is the law of conservation of linear momentum for a system of particles. Now see, you can understand this thing easily. If resultant external force, that is 0, then total linear momentum remains constant, individual linear momentum of the constituent particle may change, as well as we know if F equal to 0, then F equal to m ACM, m is not 0, so acceleration will be 0. It implies that if the system is in the motion, then it will continue motion with constant velocity of center of mass. And if it is stationary, then center of mass, that will remain stationary. See here, in this example we can observe this thing. If the heavy nucleus Ra disintegrate or split into lighter nuclei Rn and He, and if it is in motion, right, then if external force is not acting here, the individual linear momentum of these constituents He and Rn changes. Clear? But these changes will take place in such a way that the total linear momentum, that remains constant, and when it is in motion, the center of mass of the system will continue the motion with constant velocity. If we consider this second case, in which if Ra, that is stationary, and it is splitting in two lighter nuclei He and Rn, so again here we can say the linear momentum of He and Rn changes. Initially when these two were the part of system, at that time their linear momenta was 0. Now they have some linear momentum because they are flying in different directions, right? Okay. But here this change in the linear momentum of He and Rn will take place in such a way that the total linear momentum of the system will remain constant. Means before splitting and after splitting, total linear momentum will remain same. And here system is stationary, means acceleration is 0, right? So after splitting also, the center of mass will remain stationary for a system of these He and Rn, two constituent particles. Clear to all of you?